Okay. Welcome, everybody. This is John Berry speaking, and for our speaker for the AIPG Texas Section Seminar this month, we have Brian Smith, who has been the Aquifer Science Team Leader and Principal Hydrogeologist at the Barton Springs Edwards Aquifer Conservation District here in Austin since 2001. He's guided the science program to support policymakers in management of the aquifers within the district. Most of his 35 plus years of professional experience have involved the study of karst and aquifers developed in karst. So I will, that's my introduction for Brian. And if you have questions that come up during the talk, I will be checking the chat box. So if you just type them into the chat box, and then Brian, if you feel like addressing any of those things during the talk, you may, but I recommend actually addressing all of them at the end if that's what you prefer.
Okay, yeah, I think that'll be best.
Okay, let's go. Thank you.
Okay, well, thank you and welcome to everybody. Just one note, because I have this pointer turned on as a laser pointer, kind of limits me from using it as a mouse. So I won't be able to see the chats for now until maybe I close up the PowerPoint. So I'll just kind of go through, and I guess if John, if you need anything, you can speak up or wave, and we can interrupt things to answer a question or deal with a technical issue, which hopefully we won't have any problems with. So anyway, with that, I'll read my title. It's a little change from what was published, just to focus a little more on just what I'll be talking about. So multi-port well monitoring and recharge enhancement of the Edwards and Trinity Aquifers. And that's really, we're looking at South Austin, Northern Hays County, and some areas just beyond that where we at the district have been working. The district's been in place for 35 years, and I've been working there for 22 plus years. So anyway, I'm glad to be here and be able to present this. Let me just jump to my outline. So what I'll be talking about is giving an introduction on the aspect of what is a multi-port well and what are the other ways to monitor complex aquifers and multiple aquifers. Then I'll give some examples of some wells that we've done around, the Austin, Hays County area, and even give a couple of slides on some site in Puerto Rico that I worked on some years back with the Karst Belt, where we installed numerous multi-port wells. And then I'll talk about recharge enhancement of the Edwards Aquifer and even tie in how we're using these multi-port wells to help us understand better the influence of recharge, especially where we're enhancing recharge through a particular cave. And then, as John said, we'll have time for questions, right at the end. So I'll try and keep this on time and give us time for questions. And so with that, we'll go on to, okay, so just a little background on who we are as a groundwater district in Texas. There's probably about, I guess, 100, and could change at any time, but about 100 groundwater districts in Texas, and largely they can regulate groundwater within their areas, but each of them have some slightly different rules, even though most are under Chapter 36 of the Texas Water Code. But anyway, you can see in the upper part of this map, we have the city of Austin, really covers a large area here, but this is downtown where the star is. And just see just across the Colorado River is Barton Springs. So many of you probably have been there and dipped your toes in and said, oh, that's too cold. And then, just sit on the bank and watch the other swimmers enjoying the cold water. So our district continues all the way down to the southern end of Hays County. And that's really only recent that we've had that much of an area. So the southern area, we call it the annex area, and that's where the Edwards Aquifer Authority out of San Antonio has authority for the Edwards in this area, but Barton Springs district has authority for any other groundwater in the southern portion. Whereas north of this dotted line along Highway 150 coming out of the city of Kyle, the Barton Springs district has authority to regulate groundwater of any aquifer within here. So Edwards, Trinity, Austin Chalk, and you name it, we have the authority for that. So what you can see from the map, this area here, kind of purplish area is the subcrop or the confined portion of the Edwards, where there's very low permeable rock sitting on top of the Edwards units. And west of there, we have the recharge zone. So there we have the limestones, dolomites of the Edwards exposed at the surface. So we get direct recharge in that area. And then we go further west, this kind of yellowish green is where Trinity geologic units crop out. So that's where the Trinity aquifers are. And it's also called the contributing zone to the Edwards because so much water that lands and rainfall that lands on that area flows into streams. Those streams cross the recharge zone and then recharge the Edwards. So we get a lot of spring flow out of the Trinity that then comes back to the surface, flows along a creek. Say Onion Creek is in this area here and recharges the Edwards, and then it comes out at Barton Springs, or if it doesn't get pumped out by a water supply well. So you can see here's the Travis County and Hayes County boundary that cuts across to the southeast here. And this outer area is over the saline Edwards. So no one's really pumping that water to any extent because it's very saline, but people in that area get fresh water from the freshwater Edwards, and it's just piped out through water purveyors to that area. Okay, now this is just kind of a very generalized cross-section and stratigraphic column. So if we look on the left, we're talking about lower Cretaceous geologic units. So we have the Edwards Aquifer that's made up of the Georgetown Formation at the top, and then the Edwards Group. And below that, we have the various Trinity units from upper, middle, and lower, and we think about which aquifers. And then you see here's a geologic cross-section showing some of the wells that are out there, showing the faulting associated with the Balcones fault zone. And this cross-section follows this line kind of near the Travis, Hayes counties. Okay, I'm showing this one. Now, this is much more complex, so let's not worry about specifically what's there. The key message is the Trinity is very complicated, really much more so than the Edwards. Again, it shows lower Cretaceous, Trinity Group, and we have these various units, Glen Rose, upper and lower, Ensel, Cow Creek, Hammett, Sligo, and Hoston. So we've put in wells, monitor wells through various units here. One thing I will point out, though, because this is very important to how water flows and water quality, you see in this middle part of the Glen Rose, really the lower part of the upper Glen Rose, are these evaporite beds. And these are very common throughout. So they influence the flow of water or prevent flow of water, and they also contribute to high total dissolved solids. And as it shows here, they form an aquitard. And we go down a little further, and the Hammett is largely a clay that it too is an aquitard. So these are all very important hydrologic units in this study area. Okay, so I'm going to talk about multi-port wells, multi-level and conventional monitor wells, and what they are, what the benefits are, why we might use them, and what we can get out of them. So this first slide, it's kind of a scatter shot. Let me lead you through a little bit of what we're seeing. So this is in central Hayes County. There's about 65 wells that we did a synoptic water level measurement in March of 2015. And you can see on the left is water level elevation going from 600 down here to 1200. So we're kind of looking a long strike. So this is kind of really a dip section going from higher levels to the left to lower to the right. And there's some longitude here that's kind of, unless you're really into these numbers and GIS, they probably don't mean much. But this is looking at a length of about 6 or 7 miles from the left side to the right side. And we're compressing all these wells that might be in about a 4 or 5 mile distance as we look in. So we're trying to figure out, well, what's going on here? We had an issue with a water company coming in and wanted to pump a large amount of water out of here. And people were saying, well, yeah, I don't know if something might happen, bad might happen to these wells if a huge amount of water is pumped. So we did some studies. So from here, you look at this, say, how do you sort this out? How do you sort out the scattering of water levels that along, one view of this, you might go 300 or 400 feet of different head differences. Now we made this a little easier by trying to sort out by color what some of these are. So these red ones, Middle Trinity, largely the Cow Creek Formation, where we had some completion data of wells, but very often we don't have data. Go talk to many well owners, say, I don't know, I get water out of it, I don't know how deep it is, what unit it's in. So that makes it harder for us to figure things out. But we had some idea for many of these. And also many of these are open to various subunits of the Trinity aquifers. So we were trying to figure out how do we make sense of this complexity. So we thought, well, a multi-port monitor well, which you had already installed several in our district, and we installed one then in this area shortly after this synoptic measurement was done. So with that in mind, just knowing whenever you look at some aquifer, taking data from an aquifer, trying to interpret it, think about how complex it really might be if you were to dig in a little further. So here's an example of just showing what we might be dealing with. So you have a site that you're new to, and like, you know, a little bit of geology, maybe you know there's 3 geologic units, but maybe not a lot about the hydrology. So think about, well, we might have something going on here we need to understand. So you might put in multiple wells, like let's see what the upper part looks like, put in a monitor well there, put another one. Now this one actually shows screens going across here. Let's just say if we screen this middle one off just here, then we're looking at this middle unit, and say another one over here on the left. So we complete those as well, start doing, you know, water quality sampling, head measurements, slug testing, hydraulic conductivity, start to get an idea of what we're dealing with. But it could be much more complex than that, or maybe not. So this is where we can go from nested wells, 3 nested wells, say very close to each other, to a single borehole, and put in the special devices, these multi-port devices. And here, let's say we put in 6 zones. That's still not a whole lot of zones, but we're going to get a lot more data out of this and a lot better understanding of what's going on in these units. You know, where there's permeable units, where there's low permeability. If there's contaminants out here, we can get an idea of where they are, how they're moving. And I'll talk more about the specifics of how these are done. But for now, I'll just say, yeah, these zones are separated by packers that are installed in around the casing inside, you know, the borehole. And here's another example. This is what we even really call multi-level, where we have a single borehole. And this one's completed in the Cow Creek Formation. This is one we installed just about a year ago out near Wimberley in Jacobs Well area. So this is open hole. Then where we had this riser pipe, we sealed that off. There's a rubber packer there that held back the cement seal. And so at this depth of, says gravel pack, 160 to 194 feet. So we put in a 1-inch piezometer, 1-inch PVC pipe that was slotted. Whereas this pipe here was not slotted, just solid 4.5-inch PVC pipe. So that makes it the main part of the well. But then we installed a piezometer, backfilled it with gravel, and then filled it with cement again. So essentially, when we're looking at water levels in this piezometer, we're really seeing what is the water level, what is the pressure in this portion of the hydrologic units that we're measuring. And we've even done some of these where we've had, you know, 3 zones. Maybe you can even do more than that. You can only put so much down a borehole, so it can get a little complicated over time. But we've done others, and we worked with City of Austin on a well like this, and Hayes Trinity Groundwater District to the west of us has also put in some wells like this. So this too is very useful to understand, particularly here where we're looking largely at water levels, but you could configure these for sampling and other testing. Okay, so here's another example. This is really where we started with our investigations of how does the Edwards in our area relate to the Trinity, which is, you know, much deeper, you know, below the Edwards. So we actually found in an old abandoned quarry, there was an old water supply well from the Trinity. That's what this well is here. The Trinity well, it went down, you know, about 1,000 feet to where it stopped in the Hammett Shale, but it's open to a number of these units here. So we decided, well, we need to figure out what the Edwards is doing. So we installed just a standard, very simple monitor well within, this shows 40 feet away from that well. And so we got water levels in the Edwards, we got water levels in the Trinity, and I guess this already gives it away, downward vertical flow potential. But now let's look at how those numbers stack up. So here we are. The upper hydrograph is the Edwards. Lower hydrograph here is the Trinity. And we see right at this point in time an 85-foot head difference. And that kind of stays somewhat the same, but you can see these patterns don't match up ideally, but then, they shouldn't be expected to, considering, the different geologic units that they're completed in, but they still follow similar pattern, wet times and dry times. So we're still seeing this, 80, 90-foot head difference between them. So that indicates there's some serious aquatards in there, some units, very low permeability that's keeping these separate. So this was our first glimpse of saying that, okay, the Edwards and Trinity have a good potential of being separate. And I'll just mention now sort of the reason why we as a groundwater district who regulate these aquifers wanted to determine that. We were looking at putting severe restrictions on use of the Edwards. And yet some people are saying, well, if you do that, you're just going to pull water from the Trinity. And that water is different water quality. It could interfere with the Edwards. So well, that could be, but let's look at it closely. So we ended up with 3 well pairs like this with Edwards and Trinity wells and seeing sort of a similar pattern. So from there, we got into installing the Multiport wells. And so here's again a glimpse at sort of another view of the same kind of set of geology from the Edwards here, and then in blue, Upper Glen Rose, Lower Glen Rose, penciled down to the Cow Creek limestone. So making up the middle Trinity, Upper Trinity, then the Edwards. And this shows how we can divide this into multiple zones. And so now I'll talk about some of the installation process and how we collect data before I get into what does all this data really mean? What is it telling us? So of course, well, we're going to have to drill a well. But to put these systems in, ideally you want a small diameter borehole. 4 inches is what the West Bay people, I should say, this is from a company out of Vancouver, Canada, that supplies the material and a lot of the logistics and technical aspects of doing these wells. And they've been in existence for over 40 years and been putting these kind of wells in, around the world. So anyway, you start out with a very narrow diameter borehole. And you can go larger. They have some equipment that is designed for larger boreholes. Of course, you'll pay more, but under some circumstances, you might be able to go up to 7 or 8 inch borehole sizes with this kind of technology. But we were sticking with the smaller size and actually drilling 5-inch boreholes and maybe a little larger. So anyway, so drilling is some examples where we drilled some. This was in the Saline Edwards zone, where we drilled down to 1,100 feet. Through the confining units and through the Edwards and even into a little bit of the Trinity. And I'll show some numbers later, but this little pond here is not something you'd want to swim in. It smells bad and the water quality is like over 10,000 milligrams per liter of total dissolved solids. So here's another one. This is in Southwest Travis County to a total depth of 717 feet that we put in about 6 years ago. Of course, geophysical logging, if you learn a lot from running the geophysical logs. So this helps us figure out where the different geologic units are, where the hydrogeology might be changing, and how we might want to design the well. So we do that. We look at cuttings, any other data we have. Again, here's one of the geophysical logs, the little orange dots on there as we're thinking about what zones do we want, and particularly where do we want to put the packers, because the packers will determine the top and bottom of a zone. So here's an even downhole camera, any tools you can get. Core is even great if you can get it from many of these wells. So this on the left is a picture from our Antioch well showing a fracture and dissolution along this fracture. So that shows out there's a good source of water flowing through there. To the right is in the Upper Glen Rose, and this is some of the evaporites I was talking about before. Don't know if it's gypsum or anhydrite, but it's kind of these, looks like anhydrite nodules or chicken wire anhydrite, it's sometimes called. And that's just not permeable. That anhydrite or gypsum just fills up every little pore space. So you're not going to get water moving through there very easily, if at all. But it can contribute to poor water quality with the sulfates and dissolving and causing high TDS. I should also mention that we have a similar picture from the Middle Trinity at a depth of about 1,300 feet to this one on the left, where we saw fractures and dissolution. So even in that depth, we're dealing with karst, which is, again, karst is, dissolution of limestone and dolomite to increase the porosity in some way, often forming caves and sinkholes. Here we're looking at it as conduits for groundwater to flow. Okay, well, so we sit around the office and tell jokes and get the guys from Canada there on the left to help us figure out things. Their years of experience are very invaluable. On the right, you can see where we're scribbling in things on the geophysical log. Think about, where do we want the zones? Where do we want the packers? So ideally, you want to put a packer where you have competent borehole. If the borehole's irregular, it's not a good place for a packer. So we usually find a place where the caliper log and other indications are good solid borehole walls. So we can put a packer in and inflate it with water to seal off that. And I'll show some more of that, like here in particular. So you can look at this schematic diagram showing different units that we want, particularly this one here, this monitor zone. So we have the borehole walls on the side. This is open borehole. Then we have this PVC, which you can also see on the right. This is a mock-up of a monitoring zone from one of these multiport wells. So we have this 2-inch diameter PVC in which we connect with couplings, and some of those couplings actually serve as monitoring ports or pumping ports. And I'll show a little more about that shortly. So we install that. Again, the blue is a packer, and those are inflated, with water. So they're pretty much permanent, although our West Bay people talk about retrieving a well, but sounds expensive and problematic. So anyway, here's where we're getting multiple zones. And again, this is the equipment. Here's a cutaway of a packer. So if you imagine this like a balloon, you inflate it with water and it just swells out till it's sealed tight against the sides, the borehole walls. And it's left there indefinitely. And we've seen that these packers can stay inflated indefinitely for decades and continue to seal off this monitoring zone that we have in between. Okay, so here at Ruby Ranch, this was actually our first, the first multiport well we installed in, in our district. So you see, here's the natural gamma, the caliper log, and sort of showing where we started putting these zones. Let's see, the next figure sort of highlights the top and bottom. So where the red lines are essentially where we put in, we put in the packers and inflated those. So that's where we're getting a monitor zone for each of these numbers. Sort of in hindsight, and I should also say that, these zones can be anywhere from as thin as like maybe 5 feet up to hundreds of feet if you wanted to go that far. We actually look at this now and in hindsight say, well, the zone 10 and 11, we were limited on the money and how much zones we could put in. But in hindsight, like, oh, if we could have just put in another zone or two there, we could get a lot more detail of this transition area from the Edwards and Upper Trinity and getting down into where we're starting to get confined conditions in the, in the aquifer. So as we're installing, here's where we lay out all these components. So that's mainly 5 and 10 foot pieces of PVC. And we have packers. So these kind of turquoise blue are the packers. And then we have couplings. In most couplings, all they do is hold 2 pieces of PVC together. But certain ones are monitoring ports or pumping ports. And on the right, you can see as we're trying to install this before the storm gets there, we didn't succeed and those tarps got blown away and destroyed, and we hunkered down until the storm passed and then kept going with it. It was a nice sunnier day in maybe it's January 2008 or 9 when we first put in our first well in this area. So here we are laying out all the pieces. We've already designed it, so we have each piece numbered, and we just go sequentially through there and connect the pieces as they're lowered down into the well. So as you can see here, we're putting down the PVC and putting in couplings, and there's an end cap. So the end cap seals off the bottom, so no water is moving in and out of this. And on the right, you can see we're taking a regular coupling that snaps these two together. Maybe some of you have worked with Certalock monitor wells where these pieces snap together. There's no ring, then use a little plastic wire to physically connect them. And those things are nearly impossible to pull apart. And what we also do is we test each of these couplings to make sure that hydraulically there's no leakage at any of these couplings. So we know later this is an integrity of this well is good. Here we are on the left, just getting a packer in there, and they're kind of looking to see if any water drops are coming out. Occasionally something leaks and you reject it and get another part and keep moving with it. And you can see on the right a kind of a schematic diagram showing here's packers. They're not near as big as that, but just how they are in the ground there to separate the monitoring zones. So continuing with installation, as we got everybody putting all the pieces together, doing the testing. And on the right is where we have the system, a pump and this hose that goes down and inflates, a special device that actually injects water into a little valve then and allows the water to go inside the packer and cause that just to swell up. Once we reach a certain pressure of that water, we know that we put in enough water, we measure the volume of water going in and the pressures after we inject each say liter of water until we get to the point of that's been certified that packer is inflated to the level that it needs to be. And pretty much once the packers are all inflated, the well is done. Now, of course, you often want to go and purge a well. So whatever drilling fluids are in those zones, we'd like to purge those out. So there's a system here, say on the right, we have, this is called a pumping port. So you mechanically, from the surface, you actually open and close this sleeve. And you can't really see it here, but there is about 2 inches of screen. So it doesn't sound like a lot, but you can get a fair amount of water moving through there. So you pop this open, you put in a pump that'll purge the water out and that'll pull the water from the annular space here and pull it up to the surface. So you can clean up, as you would for a standard monitor well. As often the regulators want you to, the standard really to take out the drilling fluids and get back to the native water in the zone. So in this, depending on the permeability, you might pump this for a few hours, might take all day to purge water out of a really tight zone. And here's a couple of completed wells. It's a steel casing stick-up protective casing around a concrete pad. These can also be installed with flush mount. Doesn't have to be sticking up like this, but that's often the easiest way to complete it. And in the case on the left, when anybody driving into us, put these protective posts. And the second one, well, we weren't too worried about the burros and the cows, and the owners of the property put a big ring of rocks around there. So no one was going to drive over our well. So now we have the whole system in place. We're ready to start collecting data. So we look at long-term data. We can collect the fluid pressures, which we then convert to water levels, potentiometric levels. Hydraulic conductivity by form of slug testing and sampling. So we can take samples out of these wells. And for all these, we can go back anytime and do these in the future. So here we go we have a wireline tool. So we see it in these two figures, one of which is this is being lowered down the well. It's only about 2 feet long and it's on a steel cable that sends an electric signal to the surface. And there's a cutaway of one of these measuring ports. So what we have to do to measure and take a sample, measure pressures or take a sample, we have to line this, see this black O-ring here, that has to line up exactly with this little bead, metal bead here, which is your sampling valve. And that has to go down 100 feet, 1,000 feet, whatever, and face in the right direction. You think, how do you know when you're down there? Well, the system was designed by some smart people that figured this out, and it works. It's just, really actually pretty simple how it does that, how it knows what depth it is and how it rotates to get into place. And once it's there at that point, you activate a shoe that will push out on the backside and push this valve, this O-ring up against the valve, and that will actually open it. Then you have a pressure transducer inside the tool that's measuring, the actual pressure of the formation, or of that annular space, which should be pretty much what the pressure is in the formation. So you start recording what that pressure is and doing calculations, come up with here's the potentiometric pressure of that particular zone. And then say if we're going to collect a sample, we throw another switch which activates a valve inside the tool that lets water from the outside flow through a little tube. And I'll show a picture here in a second, probably. Well, it'll be just coming up just after this, but that's where the water then flows into your sampling devices, and you let it sit for a couple minutes till it's filled up and pull it to the surface. So here on the left, we have somebody doing a slug test. So they actually mechanically open that little metal sleeve that I showed you earlier. So once that's open, then we can induce a slug. Say here in this case, we have this PVC slug on a rope to displace water, and we have a transducer that'll be placed down there, and we're just doing a standard, slug test as you would in any kind of monitor, well, or piezometer. And here's where we're back to sampling. So you can see this is laid out here. There's 4 of these stainless steel bottles, each of them holding 250 milliliters. So you're basically pulling a liter of sample on a trip. So many times that's all you need, but sometimes you have to go get a lot of water for isotopes or something, and you might make several trips. And that can take a while to get down 1,000 feet or more. Go down, open it, collect sample, put it back up. But that's the nature of groundwater sampling. It takes time to do it right. Okay, so just some examples of some of the studies we've done around the district. I'd say, again, this is a map I showed earlier, and here's 7 wells that we've installed. And so they go from, our Ruby Ranch here, so these were various Edwards / Trinity. We actually have one here. The number 4 is a shallow one, just about 200 feet deep. That's only in the Edwards, and that's to monitor recharge enhancement that I'll show in a few minutes here about how we do that. Over here in 3, this is in the saline Edwards, where we put in the well. We're going to look at feasibility of doing aquifer storage and recovery and desalination of the saline water. Then here, this number 5, that's where I showed that complex mix of wells that we were measuring water levels, trying to figure out, how does all this really make sense, and the complexity of the vertical aquifers. Then we did one just a year ago out near Jacobs Well, this number 7, and we put in one off of Hamilton Pool Road in Travis County. So with that, again, here's that same hydrostratigraphic section, and showing that section I showed before, but showing all the wells that we put in except for the one out by in Wimberley by Jacobs Well, showing various depths, various targets that we're going after. But many of these we're looking at Edwards Trinity connections, especially in the middle area here. Okay, and again, back to the same complex figure, but again, to say this is complex and heterogeneous geologic and hydrogeologic units. And the multiport wells allow detailed aquifer characterization, which is what we're trying to figure out, is determining the water resources and how much can be allowed to be pumped from these aquifers without causing harm, and how are they connected, and what is the water quality, and how that might change over time. So here's this Edwards Trinity connection. We put in these Ruby Ranch and Antioch wells. Those are both right near Onion Creek in Hays County, just a little bit outside of Austin and west of city of Buda. First one was 1,120 feet deep, 14 zones, and the Antioch one 1,375 feet deep with 21 zones. Now this is a hydrograph. So this is a little more of a simple hydrograph, even though there's a lot of zones here. If you just picture, we measured a whole lot of wells. It's sort of the equivalent of that. That's why we call them multiport, because one well, one borehole, but multiple zones. So this shows, these are the Edwards in the upper part here. These lines are all the Edwards. These here are the Middle Trinity largely. And you see that throughout time, there's a consistent difference between them, very significant difference in heads. Now we have this one intermediate zone, which is part of the upper Glen Rose, but that's also showing this transition between the Edwards, how to extent it changes. It's kind of flat in here, then we get a lot of rain, it goes up. The Trinity, the Middle Trinity responds, but a little slower and not the same magnitude. Okay, so in that same well, here's what's particularly interesting as we see. Here's the Edwards up in the upper part, and some of the Trinity, uppermost Trinity. Then we get these zones 10, 9, and 8 that are very high total dissolved solids, about 2,000 to 3,500 milligrams per liter of total dissolved solids. Then we get down into the lower Glen Rose, actually had some reef rocks here, and the Cow Creek. So these were all consistently low TDS, lower than 1,000. Kind of surprising, just going through this very high TDS zone and then getting into something very good water quality. But I think that shows a lot about where the source of that water is in the confining nature of these zones of here, 8, 9, and 10. Here's another hydrograph. These are a little harder to read, but they show kind of what we're seeing in that hydrograph just a couple slides back. So really we're looking at this by zone and over time. So it's easier to probably talk about this lower part. Say here in the Cow Creek, zone 3. Here's what the water pressure was in September of 2010. And then as we're getting into drought conditions, water levels are dropping. So then we go to December that year, February of 2011, and eventually May of 2011, which was really a really bad year for drought in this area. So we're showing that decrease as we see in the Edwards and Uppermost Trinity here. So again, these are a little hard to follow because they don't follow the traditional method of hydrograph over time, along the x-axis, but this is just another way to view the data. And in the middle, we're seeing some zones that are hardly changing. And on the right, we're seeing here's this 8, 9, and 10, very high TDS values and very good water quality below and above that. Okay, so what we've determined from these Edwards Trinity tests are that the data indicate vertical groundwater flow between Edwards and Middle Trinity is limited. Perhaps I should say very limited. We don't see water, even with faulting in the area, water is passing through there. And the policy implications are the Edwards and Middle Trinity aquifers can be managed independently. There's not a hydraulic connection that would allow some significant movement or even minor movement of water. And there was a paper that we worked with Corinne Wong from UT Austin on that's published in Groundwater. So I could always provide that reference if anyone's interested. Okay, so let's look at the saline Edwards. As I mentioned before, we're looking at this for possible ASR, aquifer storage and recovery in the saline zone and for desalination. Make a long story short, this aquifer looks like it would work well for either of those and even both of them at one time. So again, we're looking at this kind of complex, head profile, kind of showing heads here across the bottom, and we're going from, say, the red is October of 2016. So we saw that from there, water levels were dropping, throughout the saline Edwards and a little bit of Glen Rose, and then it came back up. So this is very isolated from the surface and from the freshwater Edwards, but we're still seeing pressure changes from further west, some miles to the west, that are affecting the saline Edwards. So that all leads to questions about how are those connected or not connected? How are we seeing pressure changes when we're not seeing water quality changes? But that's a whole nother talk, and still a lot to be figured out with that. Okay, so looking at the geochemistry, I'll just really focus on the right side here where we're seeing, okay, so here's total dissolved solids. This one here goes up to 18,600 milligrams per liter. And even the lower ones are like, 8,800. So it goes from very bad water to even much worse water. And yet this is about 1.25 miles from the freshwater Edwards, where we have TDS values of 400 or 500 milligrams per liter. So it's interesting that this transition happened so quickly and makes you think about what is going on, where we might have some faulting, we might not have faulting, but this is a factor we see up and down the Edwards, wherever we have freshwater Edwards up against saline Edwards, from north around Waco to down around San Antonio and west of there, we're seeing the same phenomenon. So anyway, conclusions are that, we've got very high TDS values, hydraulic conductivity. Some zones are 0.01 feet per day and up to 474. So we're seeing quite a wide range of hydraulic conductivity. But anyway, it appears to be very transmissive, and high yielding wells are possible. And there's a good potential for long-term storage as an aquifer storage and recovery system. And also the desalination is very likely here because it can yield a lot of water, and it is a little higher than you might want for TDS values, but it is technically feasible, perhaps not financially at this time, but that remains to be seen. And we published a paper back in 2017 about our findings on that. So a little more with looking at the Trinity. Here's some out in Rolling Oaks, Travis County, and Jacobs Well, we just did a year ago. So Rolling Oaks, we're seeing just Trinity. There is some Edwards there, but it's not really saturated. Here's the Walnut. It's considered part of the Edwards, but there's just no saturated Edwards in this area. So it's not till you get down here till where you start seeing, some saturating conditions. And then where we see this big kick to the side, again, this is that kind of complex hydrograph that's, looking at things in a little different way than normal. We see when it makes a drop like this, there must be some confining unit in here. So we have a perched aquifer here, perhaps another one here. Then we get down into the upper Glen Rose. We see some confinement again in here. And we get down into the Cow Creek, and that's, heads are much lower there. But we're still seeing these changes over time with wet and dry conditions in most of these units. Okay, Travis County Multiport, this was interesting. We ended up with some dry zones. What we were finding was this area has been depleted, and largely we think it's from pumping. There's no reason to think that there wouldn't be recharge getting into these rocks. We have some perch zones up here in the upper Glen Rose. Then these zones here down to the Hensel, below the lower Glen Rose, we just couldn't get water out of them. And it turns out there's a lot of people in that area that had wells from years back, and they've had to drill new wells deeper to go into Cow Creek or even into the lower Trinity, Sligo and Austin, just because these units have been depleted. They were still looking into that, saying, well, how is that much pumping going on? But obviously this well and in these zones and other wells in the area are dry and around there. So let's get on to Jacobs Well. Perhaps many of you have been out there, maybe for a nice little swim. On the left, we see optimum conditions when Jacobs Well is flowing very well. So here's this cave that just drops down, and eventually it goes down over 100 feet, and there's a conduit. Cave divers have been back there over a mile. But when we get into drought conditions and coupled with the pumping that's going on there to feed that area north of Wimberley, it stops flowing in even moderate droughts now. So here's a picture from downstream of the left picture looking up, and you see this concrete wall here is what these people are standing on here, and they're doing some chanting and so forth to try and get the spring to flow again. And actually it rained shortly after that, so I guess it worked. But you can see here that the water is just not flowing out at this point. That's what is there is probably bypassing and going through the deeper system. Just real quick here, looking at another one of these hydrographs, and we see various these various perch zones up top. Then we get down into the Hensel, which we think is largely confining in this area to the Cow Creek, which is the main target for water wells in the area and where water is flowing that eventually comes out in Jacobs Well. Then we get through the Hammett Shale, which is practically no permeability to the Sligo and Austin, and seeing how water level changes are actually more there than they are in the Cow Creek. And that's largely because the Cow Creek is feeding into Jacobs Well, and a conduit will significantly influence water levels, basically dampening the amount of water level changes that take place from wet to dry times, whereas the Austin and Sligo are reacting to conditions probably at some distance away, where again we're experiencing drought as water levels are dropping throughout the area in just this past year. Okay, real quick to jump to Puerto Rico so I can get on to real quick go through our recharge enhancement activities. So this is an example of these multi-port wells being used at a Superfund site in Puerto Rico. So for years there was industry. You can see on this aerial photo to the left, all along this highway, there was a lot of industry. They were basically just dumping their industrial solvents on the ground, or whatever they leaked out or they got dumped. Who knows? But there's a lot of industry here. So we end up with this plume of contamination. This is trichloroethylene, TCE. You see this large part of the plume here is 300 micrograms per liter. And we get down to the center part here, probably close to a DNAPL, source of the TCE, but But ultimately we found out, well, the source was throughout this area, throughout all the industries that are here. But perhaps one particular factory was probably dumping more chemicals than others. And this is the North Coast. You can see in this one figure here, this is the Atlantic Ocean coastal plain, and this whole area here is just karst of Puerto Rico. You know, the hills, caves, sinkholes. But here's what we found out by putting in 23 of these monitor wells, and this only shows like 7 or 8 of them along a cross section going north, from south to north, from where the industry was here, and a little bit west of where the top of the plume was. So we see here 200 micrograms per liter of TCE in these zones here. So we were able to map out in a lot of detail where the contaminants were. That also helps to solve, how do we pump this out? Do we pump it? Do we let it go? Or what are the treatments that you really need to know what you're dealing with to do an effective treatment system? So anyway, they're doing pump and treat of that, and they're still pumping. Some 30 years later, still pumping, and probably will be indefinitely, just to try and contain the plume somewhat. Okay, so I'm going to get into, this is what I promised before about recharge enhancement, and I'll try and go through this a little quickly so we still have time for some questions about all of this. But this is an Onion Creek. So sitting on the Edwards, top of the Edwards units, the Edwards Aquifer, some years ago, some of the people that worked at the district before I was there realized there was a cave centered, it's a very small cave, you have to be a skinny caver to fit in there. But they realized a lot of water was recharging from Onion Creek. So they built this. This is the engineer that designed this back in the mid to late 90s. And they put a valve in on this side. And this side here a valve could be placed on it, but there wasn't one. It was just sealed off. So the valve would be opened and closed with air pressure. So the idea is that the valve would be closed when the storm water is passing over. So all the storm water that's in the creek would not be going into the aquifer at that point. When it cleared up in 2 or 3 days, the water is much better quality, the valve would be open and letting that get in. So, and as the bottom says, provides more spring flow during periods of drought and increased flow into the cave. Well, if we're closing the valve some of the time, how are we doing that? But we're not letting the cave clog up anymore as it once did. So we are long-term getting more water in, but we're keeping the contaminated storm water out. Here's just a quick cross-section showing the vault and the cave beneath the Onion Creek channel, sitting in the Georgetown and the Edwards group of limestones. There's a map of the cave, so showing cross-section here, the shaft going down, crawlways off to the side where much of the water flows, recharging the Edwards. From the inside of this vault, we're looking at, here's the old valve that's manually controlled. On the left, we put in a new valve in about 2007 to 2009, which is automatically controlled. So when the system detects turbidity in the water, it will close that valve. And here's where we put in a pipe extension to measure flow into the cave, and the screen to keep out the larger debris, keep the cave from clogging up again. This is sitting there in Onion Creek where there's just very minimal flow in the creek. But what we do see by measuring water levels around there, and after a lot of recharge, we see a mound of groundwater built up around the cave, and even Onion Creek is all recharging a lot. So this shows that we are getting a lot more water into the system, and that water doesn't just all flow to Barton Springs. Certainly some of it does, as our dye tracing here in this gold color shows, but it also goes into storage. So long-term, we're getting storage that can help mitigate somewhat the next drought that might happen to some extent anyway. So here's some of the equipment. We have a gauge height, specific conductivity, looking at temperatures, turbidity, and flow. These are things that we're tracking, continuously. And now we let the system just turn itself on and off as needed. So I'll sort of get over this real quickly. We did, when we had the grant to do some of these studies, 2009, 2010, we did continuous monitoring of like 5 storm events. We actually missed the 4th storm event because we didn't have our equipment set up, but we did measure that there was a storm then. So with these 6 different storms, as you can see them labeled here, we did continuous sampling and measured for nitrogen as nitrate and nitrite, phosphorus, and total suspended solids. So please ignore all these other numbers. Let's just focus on these red numbers down here. So over those 5 storm events, we saw that of nitrogen, nitrate, and nitrate, as in, we saw 2,436 pounds of nitrogen, nitrate were not allowed into the aquifer. That water bypassed that normally would have gone into the aquifer. We had 295 pounds of phosphorus, and of total suspended solids, just all the murk and crud that's in that creek didn't get into the aquifer. 190,000 pounds of total suspended solids bypassed. So these are numbers that show, like, yeah, this system is very effective at keeping out more of the contaminants. In long term, we're actually getting more water into the aquifer because of this. So a couple of quick conclusions here. Multiport wells allow detailed aquifer characterization for these very complex systems. It's a very robust system and cost-effective for long-term data. We're still working with all these wells, and they can be used to monitor nearby pumping wells, impacts from recharge enhancement, aquifer storage and recovery, drought. You know, we're using these for a lot of things. So they've really paid off in the long run. And, you know, we also use these wells to, you know, as a technical basis for groundwater management, which is what the district is really all about. That's what we're authorized to do. And we sometimes have a little funding to do some neat studies like these. So with that, I'll open it up to questions and nice view of Barton Springs, what we're trying to protect.
Thanks very much, Brian. That was really a great talk. Very, very informative as to the degree of effort that goes into protecting our groundwater around here. But I don't see any questions on the chat. So is anybody that wants to unmute themselves and ask Brian a question? Yeah, Don, go ahead. Don, are you there? I don't see.
Oh, here, there, am I there?
Yep, that you're here now. Yeah.
I was typing too slowly. So that's because I'm pushing 60 years old and I didn't grow up texting, so my fingers are slow. Anyway, here's what I was going to write. I wrote, where does the bypass water at the Onion Creek Cave go? And then in a water poor area, would it be better to try to capture that water somehow so that you have water, even though the quality is not great? But my first thing is a question, and my second thing is, hey, did you think about that issue?
Yeah. Okay. No, those are very good questions. Yeah. The first, the idea of bypass water. We're right on the edge of the recharge zone. So once it gets past that cave, it doesn't recharge anymore. It just flows down this long meandering Onion Creek by the golf course and some parks and neighborhoods that sometimes get flooded and eventually goes in the Colorado River. So we're not really looking at a lot of volume of water. For us, it's important for the small piece of the aquifer we have, but downstream users aren't really going to be concerned about, maybe, we might have, maybe 100 cubic feet per second of water that can recharge into that cave. So, it's small in that sense. So from the downstream users, and once it gets to the Colorado River, that's sort of just a drop in the bucket for what, the volume is. Whereas I know some of the bigger springs, they're very concerned about maintaining spring flow. But we could also say that if we didn't do this, that water would just go down Onion Creek. But by doing this, we're actually getting into the ground. A lot of that sediment settles out somewhere, comes out of Barton Springs much cleaner, so it goes back into the same system. So we're not losing it in any way, and we're actually cleaning it up.
Okay, thank you.
Mm-hmm.
Yeah. Any more questions?
Well, can I ask another one if nobody else has one?
Okay.
So I'm pretty familiar with, albeit dated experience with nested piezometers, where we would drill, say, an 8-inch borehole and have 3 or 4 small diameter piezometers down that same borehole.
Uh-huh.
And so the technology you showed was way beyond whatever I got involved in the past and was obviously expensive to put in. So
Yeah.
the thing I'm having a hard time with visually is that PVC casing that you put down the hole that's basically inside of the pack zones. So
Mhm.
when you draw, so that PVC doesn't really have water in it. It's a dry casing that the monitors go down, hook up to the where you extract water.
Well, it actually is filled with water, as if
Okay.
it isn't, it would probably get crushed by the water pressure.
Okay. All right. So where's the water? So it's open at the bottom at the bottom of the hole or something.
Well, no, it's closed, and essentially, as we're installing this, once you get that whole tube down in the water, it wants to float. So, we have to keep pushing it down, and you can only push so much before it wants to pop back up. So we're actually taking just tap water and filling it up with tap water as we construct it so it will sink. And at some point later, it showed how we're purging the zone. So you're kind of taking formation water and running it through that tube. So at some point, you just have a mixture of waters in there. And you don't really worry about it as long as it's not too high or too low relative to the pressures around it. Because this is so well sealed off that when you go get a sample of water, it as I showed that little O-ring, push it up against the sides.
Yeah.
Couldn't be but a few molecules of water that could exchange there when we're getting a liter of sample. So that's it is a little hard to picture that, but it is very, very tight system.
Okay, because in my past, I was familiar with pumping test packers where we would load them up and then bring them back out of the hole and not leave them down there.
Right.
So interesting where technology is going. I don't practice every day anymore, so it's kind of cool for me to see where the technology is going. So thank you.
Yeah. Well, one other comment along that line, Don, is that we're doing this pretty high sophisticated stuff, but we did one of those a year ago, and then we did that simple system of two piezometers and one borehole, just because we don't have a lot of money either. So we use a lot out of it. So there's high technology here, and just here's the old-fashioned stuff, and you go with all of that if you can.
And one more comment. I thought the downhole camera views of the various rock formations, I thought that was pretty cool too. So
we got a lot of neat pictures and stuff.
Thank you.
Sure.
We have a question on the chat from Kurt Stanley. Any thoughts to age dating the water in different zones over time, and also looking for PFAS in various zones?
Yeah, okay. Well, let me start with age dating, because we do, when we get some funding, we often get funding from the Texas Water Development Board for doing sampling, and so we've applied it. And so we have looked at age dating of these, to the extent that you can discern relative ages. And of course we see, the Edwards is very, very young. We get down to the Trinity, and it's like, but then it's kind of mixed, because some of that water is moving through conduits, even in the Trinity. So we're getting some fairly young water, but mixed with old water. So it's kind of always hard to figure out what is it really telling us, other than, this is much older, this is much younger, and, relatively speaking to that. And we haven't done in many years, real high level water quality. We're looking at it more from drinking water and just drinking water parameters. You look at all the contaminants that can be in drinking water. And I think last time we did that, it just, large extent was in 2001. And other parties are monitoring, Barton Springs, annually for a wide range of contaminants. And I think they're also analyzing for PFAS now, but I don't have any of those numbers offhand, other than say that by drinking water standards, the Edwards Aquifer is still very good. So if you get water just before it comes out of Barton Springs, you can drink it and you don't have to treat it. But, there are trace amounts, parts per trillion of various things that you would expect.
Yeah. So another question from Tim Stone in the chat. How do you test the integrity of the packer seals between zones? Can you also go back downhole to reinflate a packer that might leak over time?
Okay, yeah, that's the packers are kind of the key to this. So on one hand, when we see a good pressure differential, and we can see several feet to dozens or even 100 feet of pressure differential across a packer, that tells you that that's sealed. You know, if it was leaking, that pressure differential would bleed away. Now, sometimes we see the same pressure on either side, but that could just be because that's what the natural pressure is in the aquifer in those two zones. So you have to look closely and see, does that make sense or not? You know, you could do some other testing. You know, you could put a transducer on one zone and do a slug test in the other and see if you're seeing anything, but still you don't really know. But is water moving around in the outside, in the formation itself? So you have to look carefully at all that and be a little bit skeptical, like, well, maybe it's not ideal like we thought it would be. But I guess if you thought that a packer was leaking, you could go back, you could get that same equipment, go back and inflate it and then see if it bleeds out. But I think you could, once you do that, you could also be measuring, say, inflate a lot of pressure in there, seeing if it leaks. But the packer itself might not leak, but maybe the formation wall isn't very clean and could let water through there. But we've seen walls that don't look ideal, but we inflate that packer and that polyurethane just spreads into it. So we think we're getting very good seals with those packers.
Mm-hmm. Do we have more questions in the audience? Oh, well, we're up to the hour is up. So if we don't have any more questions, I would like to thank Brian for a very interesting talk. I certainly learned a lot more about what goes on. My background is in metals exploration and petroleum exploration, so this is new to me, and I really enjoyed hearing about it. I'm just checking. No more questions. Okay, thank you very, very much indeed, Brian. This was a wonderful talk.
Oh, you're very welcome. And I think you probably have my contact information if you care to share that with anybody. I didn't have it on the screen, but I'd be glad to address any questions or thoughts that people have about any of this. So I'd be glad to hear from people.
Great. Thanks, Brian. We really appreciate it.
Yeah. Very welcome. Thank you.
If you do have a question for Brian, yes, just send it to me. Everybody should have, you should be getting emails from me. So send it to me and I'll forward it to Brian. Okay. Thanks very much. Thanks.
Thank you.